Hello, everyone, once again. I welcome you all to our online lecture series. In this video, I will be talking about the first order differential equation. Let's continue to watch this video to have an understanding of what it is.
This video will focus on first-order differential equations and their application in economic analysis. I am Dr. Shubham Manimohan Singh, and I'm excited to guide you through this lecture. Welcome to Mathematical Methods for Economics. This course shows how differential equations model real economic dynamics. You will learn to solve first-order linear ordinary differential equations, or ODEs, and apply them to market and growth models, connecting abstract math to real-world policy and business problems. To solve these equations, we must first put them in standard form. dy by dx plus p of xy equals q of x. P of x and q of x can be functions of x or constants. The coefficient of dy dx must be 1, so divide the entire equation if needed. This standardization is the essential first step. The integrating factor method is your key tool. The integrating factor, if, transforms the left side of the equation into the derivative of a product. if equals e raised to the power of the integral of p of x dx. This elegant technique uses the product rule in reverse to convert a difficult equation into one you can integrate directly. We derive the integrating factor by seeking a function, m, that allows the equation to become the derivative of a product. Through a series of algebraic and integral steps comparing both sides and solving for m, we arrive at the integrating factor formula. m equals g raised to the power of integral p of x dx. To find the general solution, multiply the standard form by the integrating factor. Integrate both sides to get y times if equals the integral of q of x times if dx plus c. This general solution contains the arbitrary constant c. An initial condition is needed to find the specific solution for a given problem. A key economic application is market price dynamics. Prices adjust gradually based on excess demand, modeled by dp dt equals kds. With linear demand and supply functions, this becomes a first-order linear ODE. Solving it shows the exact price path toward equilibrium. Think about how the adjustment speed k affects the equilibrium speed. Another application is the Solow-Swan growth model, where capital accumulation is dk/dt equals sy-delta k. This ODE illustrates how capital evolves toward a steady state where investment equals depreciation. The solution reveals the transition path, determining how quickly an economy reaches its long-run equilibrium capital stock. We can model the national debt time path as a first-order ODE, dddt, rd equals d, where r is the interest rate and d is the deficit. After finding the integrating factor, solving this equation gives the debt trajectory over time. This shows whether debt stabilizes or grows unboundedly, depending on the interest rate and deficit relationship. Let's solve a market price adjustment problem. The equation dp dt plus p equals 6 is already in standard form. The integrating factor is e raised to the power of t. Integrating both sides yields p of t equals 6-c multiplied by e raised to the power of negative t. As time approaches infinity, the price approaches 6, the equilibrium price. The key takeaway is that first-order linear ODEs transform static economic analysis into dynamic time paths. The integrating factor method provides a systematic solution. Remember that economic variables like markets, capital, and debt follow predictable trajectories toward equilibrium, determined by initial conditions and adjustment speeds. Thank you for your attention and engagement throughout this video. I hope you found this introduction to first-order differential equations in economic analysis helpful.